Hey everyone. In this video, I'm going to talk about linear regression and maximum likelihood estimation. In some of the previous videos, I mentioned how OLS, under a certain set of assumptions, is the maximum likelihood estimator of the linear regression model. So now we're going to talk a little bit more about what this actually means. What is a maximum likelihood estimator? And more generally, what is the likelihood theory of inference? And what do we mean by maximizing a likelihood? Okay. So, most broadly, the way we kind of think about our statistical inference is that we usually want to make inferences about unknown parameters, whether it's a regression coefficient or some population quantity, based on our observed data. So, based on our sample, for example. Okay. And so, ideally, what we would like to do is make some probabilistic statement about our unobserved parameter, which we here call theta, conditional on our observed data, which here we just call y. So based on something that is known, something that we observe, we want to make a probability statement about something that is unknown, the parameter that we're interested in estimating, okay? Now, the problem is that at least in a frequentist framework, we cannot directly compute this probability of theta conditional on our observed data, okay? The probability of theta conditional on y cannot be computed, at least in the basic frequentist framework, okay? We can, however, compute the inverse probability, the probability of observing our data, conditional on the underlying parameter theta, or conditional on some assumed theta. Okay. So instead of working with this probability of theta given y, which we cannot compute, we rely on the likelihood, and the likelihood of theta given y is proportional to this probability of y, probability of observing our data, conditional on theta. And the way we kind of describe this proportionality is we write that the likelihood of theta conditional on y is equal to k times y. This is some unknown function of the data times the probability of y conditional on theta. And this this function k of y is a constant with respect to theta, so we can kind of drop it out and write that this is proportional to the probability of y conditional on theta. Okay, so the likelihood of a parameter value conditional on the data that we observe is proportional to the probability of observing the data conditional on some assumed parameter value. Okay, and that's basically the basic idea behind maximum likelihood, is that we kind of find the parameter that is most likely to have generated the data that we actually observe by comparing the probability of observing data conditional on assumed parameters. Okay, it sounds very abstract, but we'll go through an example in a second. Okay. So in general, when kind of estimating, or let's go to so as I mentioned, the likelihood function, the likelihood of theta given y, gives us information about the relative plausibility of various parameter values, or in this case theta, conditional on the same observed data y. Okay, and that's ultimately what we want to use to kind of find our best parameter estimate. Okay. So again, when kind of competing different models or different parameter values, the likelihood function ultimately gives us information about the relative plausibility of these parameter values, conditional on the same observed data. Okay. And we'll go through an example in a second. Just a few notes that about kind of maximum likelihood and the likelihood theory of inference. The first one is that this maximum likelihood estimate is basically a the maximum likelihood estimate is basically a 1-point summary of this likelihood function This likelihood function, again, tells us something about the relative plausibility of certain parameter values conditional on the data that we observe. And the maximum of this function, the most plausible value, so to speak, that's what we call the maximum likelihood estimate. Okay, so the underlying logic is, again, given the data, we basically solve for the parameter values that make the joint probability of the data most probable. Okay, we can further characterize the uncertainty around our estimate by basically examining the curvature of the likelihood plane at this maximum point. Okay, so depending on how large or how small the curvature is, we have more or less uncertainty around our parameter estimates. Okay. One thing that we have to keep in mind is that this likelihood function is not a probability density, right? So it doesn't give us direct probability statements about how likely it is that a parameter has a certain value or is in a range of values, right? But it's just a density, okay? So it's just a likelihood. It's not a probability density, okay? And another kind of technical point is that while we talk about likelihoods and maximizing likelihood functions, what we actually do kind of numerically is we maximize the logarithm of the likelihood, because ultimately that is more both analytically more tractable and also numerically easier to work with, because as we will see, for example, these likelihood functions can be, for example, like the values can get very, very, very small, so hard for a computer to deal with, and then using logarithms is ultimately easier computationally as well as analytically. Okay. So I know this is kind of a very kind of abstract way of introducing this idea of likelihood and the likelihood theory of inference. So we're going to go through one kind of applied example that is quite trivial in some sense, but it kind of helps to understand the underlying rationale. Okay, and the example that we're going to look at is going to focus on gender representation in the U.S. Supreme Court. Okay, and what we're interested in here is we want to estimate the probability of a woman being appointed to the U.S. Supreme Court. And we'll go through basically the process of finding a maximum likelihood estimate of the probability of a woman being appointed. Okay. Under a certain set of assumptions, we can talk more about the real, how realistic those assumptions are, and so on. But we'll go through the basic logic. Okay. Of course, this is an older picture of the Supreme Court. Ruth Bader Ginsburg is still sitting here. Of course, now we have Amy Coney Barrett. But at least the gender distribution in the Supreme Court is still the same, with 6 men and 3 women sitting in the U.S. Supreme Court. Okay. Now, we want to make inferences about the probability of a woman being appointed to the Supreme Court, for example, for the next vacancy. So that essentially is a question about the probability of different theta, so different probabilities of being a woman appointed, conditional on y, the data that we observe, which is how many women there have been appointed or are sitting on the bench currently. Okay. So the point is that it's not straightforward, at least without additional kind of assumptions about, the prior distribution of this probability theta. We cannot directly compute the probability of theta conditional on y, right? We don't have a clear way, at least, without invoking prior distributions, to compute this probability of theta given y, okay? But how about the inverse? How about the probability of y conditional on theta? That's pretty straightforward, actually, if we kind of think about the underlying data generating process, okay? So we have to kind of, the first step, if we want to compute the probability of y conditional on theta, the first thing we have to do is we have to kind of think about an underlying probability model. Kind of what is the underlying stochastic component, and how can we characterize this data generating process, okay? And in order to do this, at least for this kind of course, simple example, what we're going to do is we're going to make two assumptions. The first assumption is that all decisions for appointments are made independently for each vacant position, right? So there's no effect of a prior appointment on the next appointment. And the second one is that each decision has the same underlying probability of choosing a woman. So there's one true probability of choosing a woman to be appointed to the U.S. Supreme Court, and that's our quantity of interest that we're trying to estimate. That's our theta, essentially. Okay. Of course, neither of these assumptions are particularly realistic, but we're just trying to kind of go through the underlying logic. If those assumptions are true, then the appointment of Supreme Court justices is essentially a sequence of Bernoulli trials. It's essentially a sequence of coin flips with a certain success probability. And our goal is to estimate the most likely success probability given the observed Bernoulli trials that we have seen, meaning seeing how many women are currently serving on the U.S. Supreme Court. Okay. So now going back to this question about how can we compute the probability of of observing, a woman being appointed versus a man being appointed, conditional on theta, so conditional on the underlying probability of appointing a woman, we can describe this, as I mentioned, as a simple Bernoulli trial, right? So if theta is the probability of appointing a woman, and yn is a simple dichotomous variable that takes a random variable that takes a 0 or 1, 0 for a man being appointed and 1 for a woman being appointed, then the probability of for any new appointment, the probability of appointing a woman is just theta to the power of yn times 1 minus theta to the power of 1 minus yn. Okay, so the probability of observing a woman is theta, and the probability of appointing a man is 1 minus theta. Okay, pretty straightforward. It's a simple Bernoulli trial. Okay. Now, what is the likelihood, or what is the so this is kind of one Bernoulli trial, right? But of course, we have not just one observation. We have 9 justices that are currently on the Supreme Court, right? So the probability of observing that sequence of Bernoulli trials is just, since they're all assumed to be independent, it's just the product of those individual probabilities. All right. So in order to compute the likelihood function, or the probability of y conditional on theta for all 9 justices, all we have to do is we take the product of all individual probabilities. Okay, so the likelihood is proportional to the product of individual probabilities of appointing a woman for each of the 9 seats that are currently on the Supreme Court. Okay, and each of those can be expressed as theta, the one underlying success probability to the power of yn times 1 minus theta to the power of 1 minus yn. Okay. Next, we can, rather than kind of working with this likelihood function, we can work with the log likelihood function, because the log likelihood function, by virtue of the kind of basic rules of logarithm, simplifies both for analytical and numerical kind of purposes, simplifies this likelihood function. Okay, the main reason why taking the logarithm helps us is because the logarithm will turn the product sign up here into a sum, because the logarithm of a product is equal to the sum of the logarithms. Okay, so that already helps us kind of simplify this function. There are a couple of other kind of logarithm rules that we have to keep in mind. For example, the logarithm of an exponent can be pulled in front of the logarithm, and it's just multiplied by the remaining term. So this is why we have this 1 minus yn that moves in front of here. Okay. The key point is that taking the logarithm of a function does not change the position of the maximum, right? We're ultimately interested in maximizing this likelihood function. And the key point is that we can take the logarithm and the maximum of the log likelihood will still be at the same position as the maximum of the likelihood function, given that the logarithm, well, it's not a linear transformation, it's a continuous transformation. Okay, so the maximum of the likelihood and the maximum of the log likelihood are still the same points, and so we can simplify things and maximize the log likelihood. Okay, and we'll go through an example later on in regression as well. Okay, just to show kind of the underlying idea here is are these two graphics where I basically just programmed this likelihood the likelihood function as well as the log likelihood function based on the observed gender representation in the US Supreme Court in R and plotted it. And you can go to the code in RStudio Cloud to kind of see exactly how I did it. Essentially, I just basically translated these two formulas in our code and plugged in our YNs for, of course, 3 women and 6 men on the Supreme Court, and then computed the likelihood and log likelihood for different values of theta based on the observed data that we have. Okay, and this is the actual shape of this likelihood function and the log likelihood function. We see that the value that maximizes this likelihood function is both the same for the likelihood and the log likelihood, and we see that the maximum is reached at about 0.33, so 1/3. Okay, 1/3, of course, is just the proportion of women that are currently on the Supreme Court, and that's why the result is rather trivial in the sense that the most likely probability that would have generated our data, the distribution or representation, gender representation in the US Supreme Court, is of course the proportion of women that we observe on the US Supreme Court. Okay. So despite the fact that the answer itself is trivial, this example still helps us kind of go through the logic of thinking about an underlying probability model, setting up the likelihood function based on the probability of observing the data conditional on theta, and then basically using that probability of y conditional on theta to kind of given the data that we observe, find the theta that is most likely to have generated our data. And in this case, of course, that probability theta is 1/3. Okay. Also note that what we mean by the curvature, or in order to kind of characterize the uncertainty around this estimate, what we mean by that is the examining the curvature of the likelihood function at that specific point. Okay, so depending on how basically narrow that peak here is at the maximum likelihood point estimate, that will ultimately later on give us an idea of the uncertainty surrounding our point estimates. Okay. So we did this here kind of just graphically. We could, of course, in the simple example, we could simplify this likelihood function or the log likelihood function and maximize it analytically, by setting the first derivative equal to 0. We could also, solve it numerically, using different numerical maximization algorithms, and so on. But ultimately, they will all kind of lead to the same answer, which is ultimately the parameter value theta that is most likely to have generated the data. Okay. All right, I will take a break here, and now we will kind of, after going through a fairly simple example of, just computing or estimating a probability, we will now derive OLS using maximum likelihood estimation.